Good morning, good afternoon, good evening, good wherever you are. And welcome to this SNIA networking storage presentation in our security series. This we are doing to try and introduce the idea of the kind of things that perhaps you don't think about when you're putting together storage solutions. And our first part of this series is an Encryption 101, to try and understand the basics of encryption. So before we go any further, I'd just like to introduce you to the interface. There's a couple of things you may want to do during the presentation, and a couple of things I'd definitely like you to do during the presentation. The first thing you may want to do is enlarge the screen to full size, in full screen mode. Some of the slides may be a little difficult to see, especially in that small letterbox, and you might be seeing it through your browser. So if you want to enlarge it to a full screen, there's actually a button there that allows you to do so. It's down to the bottom right-hand corner of the slides. The second thing you may want to do is actually download the presentation in PDF format. There's an attachment and links button that you can press, and you can get a copy of the presentation. The other thing I definitely want you to do is, or two things I want you to do, is ask questions and to rate us. So you've got the ability to ask a question as a presenters are presenting their material, and you also have the ability to, on leaving the presentation, rate us. And the rating is from 1 to 5, where 1 is, gosh, I wish I'd been doing something else. Which, by the way, during a period of lockdown, I think will be quite amazing if we get any 1s. All the way up to a 5, which is, this is excellent. We need more. And I will be pointing you at the end of the presentation to the more you can get in this networking security series. So those are the things I'd like you to do and that you can do. What I'd like to do now is introduce our speakers for today, and it's a pleasure. My name's Alex McDonald. I'm the Vice Chair of the SNIA-NSF, and I work for NetApp, and it's a pleasure to introduce you to Ed Pullin, who's the Product Line Marketing Manager for Intel's Quick Assist technology. Good, wherever you are. Ed, is it morning for you?
It is afternoon for me, Alex, so yeah, great to be here.
Afternoon. And also introduce you to Judith Furlong, who's a distinguished engineer with Dell Technologies. Good morning, Judy, or have I just misgeographied you?
It's afternoon as well. Good afternoon to you, Alex.
Good afternoon. Yep, that's me, got the geography wrong for everything. So these are our two speakers for today. Before we get into the presentation, just a really quick introduction for SNIA. I know a lot of you will already know this, but SNIA-At-A-Glance, with 185 industry-leading organizations. We've got over 2,000 active contributing members from those 185 organizations, 2 of whom are with us today, Intel and Dell. And we also have around 50,000 IT end users and storage professionals who make use of SNIA's website to get educational materials and presentations like this. And I'll point you to that at the end of the slide. At the end of the slide, the very last slide, contains information on where you can find more information out about SNIA. I also have the great pleasure to tell you about what the Networking Storage Forum does. Quite a lot, as it turns out. We cover everything from the fundamental technologies like Ethernet, iSCSI, NVMe, all the way up to things like virtualized storage and software-defined storage. So it's anything basically that runs over a network to a storage device that we're actually interested in telling you about and educating you on. And last but not least, the legal notice. None of us is an attorney, none of us is promising to say anything that if you use it in anger and it causes something to break into 2 parts, I'm afraid both of them are going to be yours and not ours. There are no warranties with this presentation. And we'd also be delighted if you could honor our copyright. That would be really nice too. Thank you very much, because there's quite a bit of effort goes into putting these presentations together. So without further ado, I'm going to hand over to Ed, and Ed's going to introduce us to the whole concept and the long history of cryptography. Ed, take it away.
Yeah, thanks a lot, Alex. And my hair's a little longer than in that picture here, but as I said, I'm very excited to be here. You know, what we attempted to do with this webinar is to strip down the basics of cryptography and security to, you know, the varnish here. So I absolutely get thrilled when I'm learning a topic to understand, you know, the shoulders of the giants that we're standing on here. So we're going to start with the long history of cryptography. I think through the material, you're going to see references to people that have just made breakthroughs and have, really changed the world, transformed what we think of as crypto. We're going to go, like I said, to that varnish and define basic elements like ciphers, keys, entropy. We're going to look at, just the precursors to the breakthroughs I just spoke of. Some things that we're familiar with like pop culture, we might be aware of that actually were the springboard to modern cryptography. We're going to show you the differences between symmetric and asymmetric cryptography, and that's going to all build to protecting the keys to the realm. And throughout the material, you're going to see how important cryptographic keys really are. Great. Okay, so the long history of cryptography here. So let's see how far back we go, where people understand that people were creating messages that were coded, and they were coded for a reason. So we go all the way back to 4,000 years ago to ancient Egypt, where in a tomb they found messages that they, with the hieroglyphics, could actually discern that they were trying to transform that message from how it was written originally. Later on, a few hundred years later, in the same kind of realm there, they actually found recipes for pottery glaze that the glazer wanted to keep a secret, and so he used his own crypto messages with substituting characters. Flash forward to like 500 BC, this item is called a skitali, how you pronounce that. And basically, the ancient Spartans would carry the same diameter of a rod, and this strip that actually, if you wound it around a rod of that diameter, that you would get a message spelled out through that strip, and that was a way that they could transport these messages undetected. And then in the Roman Empire days, this is something that we all know with modern pop culture, the old Tom Mix or Little Orphan Annie decoder pin, where you would turn one dial and line up a different alphabet, with the main alphabet, and then write down messages there with that decoder ring. And that's known as the Caesar cipher. You're going to see how elements of these items actually kind of played forward through the history. Okay, so let's get to some basic definitions here. Okay, the cipher, as I just spoke several times in the intro there, this concept of a cipher, what does that mean? Well, it just means that you are transforming some text to some other text through a process in order to conceal it. It's really that simple. There could be many different ways that you go about doing this. It actually does not necessarily have to be digital. There are mechanical means, etc., as you just saw with like the skitali previously. So it's just simply a transformation of some message to some other form that at a glance obscures the message. Okay, and pardon the pun, a key element of that transformation is the secret key. Okay, so you wouldn't want to create a message that was just digital noise, for example, without giving someone a means to unlock that. So the fundamental element here is you actually have this thing called a key that becomes a part of the transformation algorithm. And you'll see that key can take various forms as we go through different aspects of what could be called keys. In world that we are familiar with, keys are generated via the random numbers, and this concept of entropy is very, very important. Okay, so you might remember entropy from your days in engineering school with the second law of thermodynamics, which had to do with the randomness of like heat and energy. Einstein was a huge fan of the second law of thermodynamics, and it was one that he said that it was a law within his framework that would never be overthrown. He was pretty sure that the second law of thermodynamics would hold throughout the history of science. Well, genius that we're here today because of this man, Claude Shannon, applied this concept. He's the father of information theory, and to him, information and entropy, he could actually relate those two concepts. From the physical world to the digital world. So he came up with this concept of a randomness or a disorder in the information itself. And so there are many ways that we create this. So the goal here is that when you're generating these keys, that it's very, very important you're going to see to like have very distinct individual keys, not reusing those keys, and to make sure that the key itself is not something that an attacker could guess at. So you want these to be very random. And there are many different methods they use to create that randomness. For example, at different times they've used keystrokes on a PC, for example, or mouse clicks. Also, things that are used for randomness are like the thermal noise on your laptop itself. So it actually will take the temperature of the PC itself, for example. Things like this that create randomness, sometimes like electrical randomness. But what I found was that it was very, very important to get what you see there as the TRNG, the true random numbers that they cannot have a correlation with each other, because you want each and every session key when I'm communicating with somebody, you want that key to be very distinct. Even portions of that key, you don't want somebody to be able to guess because that is information. So, for example, if I took the temperature of an element within my laptop, that might be very close to the same temperature every time I power on. And so, an attacker could start to zero in on the lack of randomness there. Like I might be getting, very similar things. So common today is, you see the Vigenere diode there from your electrical engineering courses, like Zener avalanche noise, something that is extremely random. And there are other means as well that also take into account like electrical and thermal and also like quantum noise to make sure that those keys are distinct. If you haven't noticed, this presentation here is about keys and how important they are, and which you're going to see through the next couple of slides. Okay, so we went all the way back 4,000 years to Egypt, and I think we referenced pop culture in modern day, and there's kind of a transformation of that in between that starts the jump to modern day cryptography. So some of those examples, the Vigenere cipher. So this was a cipher that is built on the Caesar cipher, but it starts to be a harbinger of modern day ciphers, in that you would have a message, a plain text, and you would have a key. Now, what I want you to note is that the key for the Vigenere cipher is the same size as the message. So for example, if I continued, that sentence with stay safe, and I continued to express other ideas around that, and had a full sentence there, I would still repeat my key to be as long as the entire message. So what the key does in the Vigenere cipher is to basically every element has its own key, and the keyword is where you start that row column of the Caesar cipher. So each and every key starts a new Caesar cipher, and there you see the stay safe with the keyword stay home would give you that message as I went through the exercise there on the bottom. But one thing to note, and you're going to see this in upcoming foils, this means that your keys and the keyword, the message itself, are the same size, okay? And obviously, I think you can think ahead and think that is a pretty complex thing to pull off there to make sure you had these repeating keys like that. Also, I think everybody is very familiar with the Enigma machine through history, and this was a pretty amazing leap in terms of cryptography there. You see, they had these you had these rotors that you could set of dials you could set, and you also had a set of what looked like the old telephone switchboard plugs that kind of laid the foundation for a set of keys that you were providing, and a couple of major concepts here. So you kind of had this foundational set of keys that each day you were given, every owner of one of these that would be receiving the messages would be given what these settings were on each day, and they changed each day. But also, the message itself began to obscure other elements of the message. So, for example, each letter in those rotors would turn other rotors. So your message and how it developed would depend on the text itself, and that's a concept that you will see flows into our modern day security. So and this was famously the very famous events around this machine here with the Bletchley Park there, the government code and cipher school, led by a very famous scientist, Alan Turing. And what they did to crack this code was to actually invent a machine that started to track what the messages look like. And you're going to also be aware, like that the distinct individual key settings, et cetera, as I mentioned before with the randomness, were what kind of allowed them to start to understand what mechanically was happening there. And that machine that they invented was was called the Bomba that actually cracked the code of the Enigma. Okay, so symmetric cryptography. So we're going to take a look at the concepts that just flowed from the history that I laid out there. And you're going to see, so I talked about the Vigenere cipher with the key being the same length as the plain text. And so we have some stream ciphers that we've used within our lifetimes, were used for security, like the RC4 cipher here one time was just a few decades ago, was commonly used. And it was a stream cipher. Your keys would be as long as the plaintext bit. And there you see the concept that I talked about, where the text itself starts to obscure the other parts of the messages. You see, to create a synchronous stream cipher, you actually provide a feedback loop where the data itself, starts to mix in with the data as it's flowing, the new plain text that's flowing through, and affects the message itself. And that's a concept you'll see that we still have today. Okay, and then there was the advent of block ciphers, which was to take your data and work with the data in block sizes. Okay, so very, very common today is the advanced encryption standard AES. This is the basic standard that we use today. There's some shifts in that recently, but this is really the foundation of our current cryptography, is the AES. I'll go into some detail with this, but that is a very common block cipher. So basically, you will have these multiple blocks that go through individual transformations, and you work on these blocks, these 128 bits in this case for AES. I'm going to actually break this down for you. This 128 bits, you work in terms of a matrix of 4 by 4 bytes, and you start the operations of the transformation that's going to give you an output of the ciphertext. And also, as you know, we've already seen the keys become a part of that mix. Okay, so even this advanced encryption standard, while it was the modern standard, that we actually went to that standard when we found other standards lacked. So even AES had this mode called the electronic codebook mode. And what we found, and this is a classic example here, this illustrates the point so clearly, is that it's not just about the message itself, it's any information leaking at all that would give an attacker a foothold to start getting your information. So any keys or any common things that the algorithms may be doing repeatedly over and over, that an attacker could collect that information and form an attack surface against. This lays that bare, because you see, using the same key as this ECB was found to be very not secure, because you can see, while it transforms the data in this mode of operation, it transforms it in such a way that is the same across all the blocks, and effectively creates a shadow of the data that leaks information. Obviously, looking at that picture, you have clear information what was sent as part of that data set. So, and again, a serious hacker would have no problem deciphering this. So yeah, like the moral of the story is that using the same key over and over and over really just creates a shadow of the data that you want to transform, and it does not effectively provide a cipher that can't be discerned. Okay, so apologies for stating the obvious, but in all of the development of these algorithms, a main facet is that what you put through one way, you need to be able to reverse in the opposite direction. So any storage to disk, you need a method to read from disk, go through the algorithm in the opposite direction, using the key algorithms in the opposite direction as they get distributed here, and flow through that algorithm to get back to the plain text. So whatever, in developing these algorithms, there's so much science and the idea of the probabilities, et cetera, that go into developing the algorithm. And by that, I mean, there are specific characters that are more common in specific languages. For example, the English language or typical ASCII characters that you want to be sure that the algorithm obscures them, that you can't see that you're using common words or common structures through that data. So you got to be able to go through it in one direction and reverse it in the other direction. That's obvious. If you're transmitting that message, the receiving end has to have the proper keys to decode the message and run through the decrypt, in the backward direction. As you can see, it kind of clearly shows the algorithms are kind of unique. This is the DES algorithm. As I said, this was a common algorithm, the data encryption standard, and this was used for a long time, 1976, you see here, and they found that the DES algorithm was insecure. So they later went to triple DES, and you also see that it has kind of a funny key size there at 56-bit keys. Triple DES was 3 times that, I think, at 168, and I think the 56-bit, there was 56-bit and like another byte of parity, I think, that went along with the DES keys here. So triple DES was actually a cascade of it literally was running through this same algorithm 3 times, and so you had these keys, the 56-bit keys for each block there, individual keys. Now, as I said, and as you're going to see in the next foil, it's very important to make sure those keys are not the same, even for individual blocks. So when DES was found to be insecure, they put out some calls for new algorithms, and what they came up with was this. What was called the Rindle, I think, was the base of this, but it was what is known as the modern. This is, as I spoke before, the advanced encryption standard is the modern base of the crypto algorithms we use today. So there are many variations of this. Like you will hear this spoke of in a couple of different ways, where you talk about the AES, you talk about its key size, so you might say AES 128 or AES 256, etc. And then you'll talk about the mode that it operates in. There are variations on this that allow you to operate in different modes. Like, for example, the ECB that we showed, caused the shadow there in the picture of the Linux, that was a mode of operation. So what basically happens with this AES algorithm? It breaks. So again, it's a byte, algorithm there. You work on 128-bit blocks, and you see there the 4x4 bytes. So that the block itself goes into the algorithm. You have keys, and what you'll notice there is that like one key starts what's known as a key transform up top. So you provide the key that you're going to use for this common message, but as part of the algorithm and part of the modes, you actually start varying those keys. Now there are lots, like the algorithm itself puts out a key for each of these various rounds that you go through, and in these modes you go through 10, 12, or 14 rounds. And so some of the things you do with those keys are very interesting. There's this concept called a nonce, which is it means number once, and basically you provide a counter. So what becomes part of the key is actually where you are at that given point in time, a count. And the reason things like that occur with these key transformations are, as I said, you don't want to use that key more than once. So you start to provide this other variable in the key, which is a count, which also can take other properties like fields, etc. But this count, like adding to the key transformation itself, allows you to do a couple of things. For example, you don't want, there are ways to attack crypto mechanisms. They're called like chosen ciphertext attacks or chosen plain text attacks. And what somebody might do is record a message that they replay at a later time. So I don't know what you sent, but I just happened to record it, and I saw that your system took some action based on that data. So if I try to replay it at some later time, I think I can get your system to react the same way. Well, not if you have this notion of the counter modes that counts in the key transformation. So yeah, here's how the AES algorithm works. Okay, it really has each round. They're called rounds, and as I said, the algorithm goes through 10, 12, or 14 rounds, depending on the key sizes you use there. But basically, there's a byte substitution. I talked about the probabilities of data and characters that might show up more frequently in data. There's actually a table, they're called the S boxes, that for every character, they have another character that you pick that makes this more probable of a blend of data. So it just substitutes the data. These are substitution parameters, or S boxes, they're known as. That's the first thing you do as part of that round, a substitution. Then you actually take this matrix of 4x4 bytes and you do what's called a shift rows. So you shift the data in the last 3 rows by 1, 2, or 3 bytes. So substitute, shift rows. The third thing you do, I talked about this diffusion, where the data itself transforms, also transforms the ciphertext in a way that obscures the data. So what you do in what's called the mixed columns portion is that you multiply the data by 1, 2, or 3, and it's a matrix multiply. If you're a computer engineer, electrical engineer, multiplication by 2 is a shift left, so it becomes easy to do this. Multiplied by 3 is a shift left plus 1, and so the algorithm's kind of built to allow an efficiency there. And then you go through that the number of times depending on the key size you're using. And in the end, the very last one has kind of a unique, and Intel has instructions for the AES, and you do something different in the last one, that the mixed columns doesn't exist in the very last round that you go through. So that is the basic of the modern day crypto here. So, okay, so you also might hear of hashes or message digests. And one thing to note here, the hash or the message digest is really used as a fingerprint over the data. So what you want to do is create a unique fingerprint across your data. You want to actually do this calculation on your message such that if somebody changes even one bit in that message, that calculation says at the receiving end, it says, wait, something went wrong. This fingerprint doesn't match what I should have gotten from a fingerprint of this message. And that's many ways how you do integrity checks, okay? And they call this, strong collision resistance. So any given two messages, you don't want to have the same fingerprint. And you could see how this would be useful in so many ways. You could have, for example, in storage, people use the hashes in storage for things like data deduplication. They also use them to tag particular blocks because each particular block would have a unique hash message. So you actually might store blocks of data and seek for that hash message for given blocks within other blocks. And also, of course, for communications, if somebody took your message and decided to put their name like it was from somebody else in an email message, when you check the integrity of that, you would find that it failed, that somebody had substituted in that message. Now, there are different protocols, and our other series are going to go into how these protocols work, but different protocols will handle the hashes in slightly different ways. So there you see like the TLS does message authentication first, and then it encrypts the entire thing. And then IPsec, for example, encrypts the data and then does a hash over that, okay? And typically, it is thought to be more secure to do the encrypt first and then the hash. Okay, so asymmetric cryptography. All right, and this gets into something that we actually touch every single day. Every time you go to any encrypted website, which is most now, you are working with asymmetric or public key cryptography. So I'm going to go back because there you go. Okay. So how this works, public key cryptography and asymmetric, what that means is that the key that you encrypt with is not the key that you decrypt with. And I absolutely, if you want to study cryptography, it's amazing to get into this history because the math for this, for example, there are two basic forms of this. There's what's called the modular exponential. These are things like the RSA. You already saw Rivest in the RC4. Ron Rivest was one of the people that invented the RSA. RSA stands for Rivest, Shamir, and Adelman. And basically, this is you take your secret and you raise it to the power of a public key and a private key. And each of these keys is in today's standards, they want these keys to be 2,000 bits. At one time, it was 1,000 bits, but today they're 2,000 bits if you're using the modular. And the way this works is there's a relationship between the public key and the private key related to prime numbers, and that relationship, when you raise the secret, which is your session key, to that power, you actually get the secret back. So you could be, and it's a bad time for me to use this example, you could be at a party and say, hey, I want you to send me a secret message. Here's my public key. The public key is public. Everybody can hear your public key. And then you decide, okay, I'm going to use this random number for our secret session key. We're going to exchange information, and I'll encrypt it with your public key and send it to you. Nobody else, even though they know my public key, even though they heard it, without my private key, they can't decrypt this. Just very quickly, there are other methods. As I said, the RSA is approximately right now, what's thought of as secure is about 2K bit keys. The elliptic curve cryptography is built on these they're literally curves, and each type of key you use has a curve of that form you see on the screen there, with the the x cubed ax plus b, and you use these curves, and you do the public and the private keys have relationships based on these point additions and these point multiplications on that elliptic curve. So again, and this is actually gaining and popularity, very popular. The types of elliptic curve keys is that you could use far fewer bits. As I said, 2,000 for the modular, like the RSA or the Diffie-Hellman type keys. That's the order. For the elliptic curve keys, you can get similar security on the order of like 256 bits, like somewhere between 200 to 500 bits there. For elliptic curve keys can have the same security properties as the RSA. So they're up and coming. Many times they do what's called perfect forward secrecy. They actually use those two together, one key protecting the other key. Okay, and this is the foundation of our modern communication. Okay. Alex, here we go. Okay, so public key cryptography is the basis for managing root of trust on the internet. As I said, you encounter public key cryptography every day when you go to a secure website, which is most. If you see HTTPS or the lock on a website, you're in a secure session with a proxy server or a CDN, somebody serving you that website. You're in a secure session with them. And the way that secure session is developed is through public key cryptography. Now, one thing that is very dangerous is that you don't want to go to a website where you think you are talking to the vendor that you're shopping from, but really you're giving somebody your credit card. So the way that you manage this is you actually authenticate that server. You actually have some element that you trust tell you, yeah, that person, that entity is who they say they are. And the way they do this is through root of trust and certificates. So how does this work? So today, if you look at your browser, you have many certificates loaded from vendors. And what's hidden in those certificates is the public key of the vendor that you are talking to. So how this works is this. So, you know, if I'm an entity, I get a certificate that says, yeah, hey, I go to the certificate authority. They give me a certificate. They build out this certificate with a bunch of information that ends up being signed with their private key. So they load, it, you know, in the certificate they give me, they load Bob here, his public key, and they sign it with their private key. And so when I want to check to see, hey, is this guy I'm talking to really Bob? I get, you know, his certificate, and the certificate authority, I get their public key, okay, and I decrypt that certificate with the certificate authority's public key, and from that, once I decrypt that, what I get in return is Bob's public key, and I can test Bob's public key, which was I just retrieved from that certificate. The only way I got it there was from that certificate, to the one that this entity I'm talking to, who claims he's Bob, he said, hey, here's my public key. From the certificate authority, the certificate, I go, oh, yep, that is Bob, because those public keys match. So I'm talking to Bob. So this will show you how important this root of trust, and how important, think about the private keys here, how important it is to keep those private keys secret. Bob's private key, the certificate authority's private key, you know, any entity that I am talking to that, you know, is actually communicating on the internet at all, their private key actually is the key to their entire realm of information. Okay, and I think with that, we'll go over to Judy and talk about the importance of protecting those keys.
Thank you. So, as you noticed in a lot of the examples that Ed took you through, the key material is obviously appears all the time. It is actually the part of the applicability of cryptography that is unique for every transaction. When you're running, the algorithms are well known and publicized. And obviously the intent is to protect that key information using that algorithm to transform it. The keys are obviously what make it unique for each transaction. So if we actually want to ensure the information that we're protecting is effective with cryptography, then it's very important that we're actually protecting key material itself. So the whole topic of key management is basically focused on what do we do to need to protect keys from threats throughout its life cycle, and ensuring that we always have the keys available when we need them. Because if we've encrypted data and we have lost the associated key material, we've now rendered that data unrecoverable. And obviously that is not something that we want. So it is both important to have availability as well as protecting it. Now, what goes into actual key management is a fair bit of technology and capabilities, and so much so that we obviously didn't want to cover it in depth in this particular presentation, but we do have a subsequent webinar in June that will go a deeper dive in the various aspects on key management. But what we did want to cover is essentially kind of at a high level, there are different approaches around key management. that are taken for handling symmetric versus asymmetric key material. Symmetric, where you have a single encryption key that is used for both encrypting and decrypting. That is something that we want to ensure that is always protected. And how I share that, so if I wanted to send information to Ed, how I could do that, it's a simple, maybe out-of-bands mechanism to do it with one person. But if you start thinking about an internet scenario where you're talking many devices talking to another set of many devices, that scalability and concerns are where you get into the different aspects of key management and how to make sure that it's a scalable solution, that we can share secret information like these keys across a variety of different protocols and a variety of different deployment models. On the asymmetric, now Ed did take you through a little bit of with asymmetric, there is an associated public and private key pair, where the public key is computed from the private, and it isn't possible to basically, if you have the public, you can't reverse it, get back to your private information. So in theory, it can be made available and public to the world. But if I just publish a public key to somebody, who says an attacker can't, I says it's Judy's key, but in reality, it's really Julie's key, and somebody else's and has substituted it. So this is why you have the public key infrastructures, the certification authorities, where they're basically a third party concept where they're attesting that it is really Judy's key that is being presented here. And there is a whole process, and we can delve into that later in the future webinar, where there's basically how we authenticate the prove that it's my key when I present it to a CA. So they're attesting it, authenticating this, and making this binding. So the key and what we see in reality with encryption, and we can certainly talk about applied cryptography, these concepts of both symmetric and asymmetric often get used together in common protocols, in various implementations, like how we do data at rest encryption, and et cetera, in our offerings. So this is basically, these often get used together. The key management often used to protect these is a combination of both technologies. So one of the other things around when we talked about keys and the cryptography and that is you also have to think about how is cryptography used in a particular, say, a product. There's probably things done for communications. There's probably done for data at rest. Each of those have a look at different mechanisms used, either symmetric or asymmetric is chosen as the method, either due to key sizes, performance, variety of reasons, or as I said, they're often mixed. And then what you want to make sure, part of this deployment scenario is you always want to make sure keys are available when you need them to be able to reverse the process. So that means you have to match your key management solution to how the encryption in cryptography is being used for different purposes within, say, a product. So that means often if you're a very highly scalable multi-node components, you need to make sure you have a key management scheme that is also scalable and accessible to every node in that environment. So this is kind of, I will obviously in the future, this webinar, there will be basically kind of more delve into that, but to just give you a feel for protecting keys, understanding that you can't do the key management independent of understanding how the cryptography is actually being leveraged. And you need to match it to the appropriate communications or data at rest or data at flight capabilities that are being leveraged. So with that, we just wanted to take through a couple of conclusion remarks. I think we saw it from a historical perspective. Cryptography is always an evolving scenario, and it's adapted over time as technology and communication forms have moved significantly, and obviously where we are in our digital age. And they are constantly being adapted to deal with new threats and to take advantage of new technologies and new mathematical techniques. The cryptography from a symmetric perspective, single key. Same key used for encryption and decryption. With algorithms and then the modes explaining how the keys are combined with the data and affecting how that happens in the algorithm. Hashing algorithms used to produce a fixed length message digest that is then can be used for basically for authentication purposes, data integrity checks, and for a variety of different capabilities, often combined with other things like in a digital signature so that you have a fixed length and a static size item that you're always signing. Asymmetric, public and private key pairs, mathematically related. Private is obviously protected in the same way as your symmetric keys, but public can be shared, but usually in a way like in a certificate where there's an attestation that this key really belongs to the person that's presenting it. And with asymmetric, you can leverage it for encryption purposes. Similarly to symmetric, it also gets used in digital signatures, where you have the capability of a public key. The private key is known only to me. I can use that to encrypt data or digitally sign data, and then the public key can be used to verify my signature. So that's another interesting point about the public key techniques. And then last but not least, a little bit about key management it's not a little scenario. There's a lot involved with it, so much so that we will take that through and discuss that at a future webinar. So with that, Alex, I think I turn it over to you to give us some wrap-up information.
Thank you very much indeed, Alice and Bob. That's a really bad cryptography joke there. In fact, I'd like to thank Judy and Ed for taking us through. I'm the only person laughing at it, I know. I'm sorry. Anyway, I'd like to thank Judy and Ed for taking us through this Encryption 101. We have a number of questions which I'm not going to ask now because we're pretty close to the top of the hour. But we will answer in our blog. You'll find I'll put up a link to the blog, and we will answer the questions there. And in fact, the questions are not what I would describe as 101 questions either. So perhaps they're not appropriate here, but we will answer them for you. In terms of what Judy was talking about, there is a new series that we're starting. You can see the Key Manage one in particular is on June the 10th. The link is there. If you follow that, you can register on Bright Talk. And we also have this series that we're planning that takes us all the way through applied cryptography, all the way out to security regulations, things like GDPR, and securing systems and hardening. So there's a whole range that we're going to be talking about in terms of security, in terms of privacy, and in terms of just making sure that modern storage systems stand up to the kind of things that we demand of them in the modern age. So those are the links there. And lastly, after the webcast, you can go off to the educational library and pick up other presentations that we have on storage, particularly those from the NSF. And as I say, we'll post the questions and the answers to them on our blog. I'd love you to rate this presentation. I'd love you to rate it on the way out. Remember, it's 1 for goodness. Even in lockdown, that wasn't worth it. All the way up to 5. Yeah, this is what we want to see, and we'd like more of this, please. Any comments you have as well, please make them. The comments help illustrate why you're giving us the score you did, and that would be incredibly helpful. And in the meanwhile, I'd like to thank everybody for attending today, and I'd like to re-thank Judy and Ed for their presentation on the fascinating subject of cryptography. Until we meet again, take care, and thank you very much.